Okay, I leave you the microphone. Thank you, Alexis.
Thank you, Loic. So I'll try to make it quick because everyone is hungry. So the thesis subject is metamaterial conception for aeroacoustic application. It is supervised by Marianne Galland at LMFA, Didier Dirna, LMFA, and Mohamed Ichou, LTDS. This thesis is funded by Celia, which is why I'm presenting here today. So my presentation will be organized as follows. First, a bit of context. Then I will present the objectives of the thesis. And then I will detail the material characterization and optimization. I will end with a conclusion and the perspectives for the ending of the thesis. So aeroacoustic applications. So this describes an acoustic treatments placed parallel to the sound propagation. This appears, as you can see, on air cooling ducts isolation, and the main work of our laboratory at LMFA is liner of the nacelle airplanes. So in these conditions, there could be the propagation of modes in the ducts and a background flow which complexify a bit the calculation and the properties. So to perform this kind of to perform this kind of absorption, we use for now perforated phase sheets and honeycombs, which have a resonant absorption in the frequency of the airplanes. So to change a bit the performances of this material, metamaterials are a lead for further evolution. So they are characterized by a periodic or a gradient evolving structure, and they differ from classic porous materials because of their structure and control geometry, which is an input of the added manufacturing techniques. So as you can see, there is a different type of metamaterial, and they're able to achieve a very sub-wavelength absorption, so low frequency absorption, but in narrow peaks due to their resonance, So the objectives of the thesis is to develop a finite element method model to perform parametric study. This will lead to the creation, we hope, of a broadband absorbing metamaterial around 500 Hertz. And we hope to do experiment and model in ducts without and then with the mean flow. This all is the creation of laboratory toys to study the sound absorption. So even if we're talking about a sound propagation parallel to the treatments, it is easier to characterize in normal incidence the acoustic device. So we use a cone-tube experiment with a rigid backing to obtain the absorption coefficient and the surface impedance. So this leads to the creation of different samples. So we start with the device by Thomas Zielinski. He creates one pore cell design. It's some kind of porous material with this unit cell propagated on all the materials. To target lower frequencies, we enlarge the cavities to create resonances, and then to investigate the way sound propagate in this material, we try to add other cavity to infill the tetraedric and octaedric spots of the material. It's a crystallography it's a crystallography stuff. Yes. And to increase the infill, the porosity and the tortuosity with oblique channels in the materials. So to present the finite element model, we make the assumption of a rigid wall. So we only represent the fluid. We use as many symmetry as we can to save time and memory. And on the lower part, you are looking at the total dissipation mapped, color map. So we had thermal and viscous dissipation. It's in logarithmic scale. This kind of dissipation, thermal and viscous, which appears in the boundary layers, are taken into account by the Navier-Stokes linearized equations with some no-slip and isothermal condition on the boundaries. So I point out that the thermal boundary layers appears on every wall of the structure, while the viscous boundary layers appears near the pores where the velocity gradient is the highest. So we've realized few materials. You use two main techniques to do so. So the fused deposition modeling, which consists of a fused wire of plastics which draw and extrude the part, and the stereolithography apparatus, which consists of polymerization of a resin which is in the bus. This comes with pros and cons. So the FDM allows to do larger samples, but it's less precise. And the SLA makes precise and small dimension features, but it's time demanding and more expensive. We compare the absorption coefficient of the frequency of the SLA, FDM, and the model, a finite element model. So you can see that there is a quite good accuracy of the prediction. And the differences are mainly due to the some difference and on the geometry realization due to the 3D printing. You can see that the FDM is less accurate because of the low definition of the geometry, and we are supposing also some kind of small scale porosity in the material due to the melting of the different wires one next to the others. So we try different geometry effects with the. So as I say, we model different parts inspired by crystallography. So we are based on two centered face crystal, and then we infill the tetrahedric and octahedric spots to increase the porosity and try different orientation for the channels. So we increase the tortuosity, and it gives interesting results for the octahedric parts in red. So then the aim of the project is the modeling in ducts. So this is the experiment setup. We try to first model it in a 2D geometry. So the two perfectly matched layers mimic the anechoic ending of the experimental setup. We generate a background pressure field here, and you are looking at the instantaneous velocity field in logarithmic scale here. As you can see, the gradient of velocity appears in the small channels where the dissipation takes place. This color map leads to the conclusion that we need to model the whole geometry, and we cannot base our measurements on just the model on just an impedance surface or fluid equivalence modeling for the absorption, like it is done with other materials like the porous classical materials, because of this very local comportment. So, as a conclusion, we've made some incomes with the printing techniques characteristics, and we point out the added manufacturing dimension limits. So there is some geometry influence on absorption we've pointed out too, and we are trying to go further in the optimization of the geometry. And then it's necessary to model the whole geometry in the case of a duct. So for the perspectives, so as I say, further experimentation, 3D duct model to take into account more specifically the behavior of the material, and then to do measurements in the Cayman duct, the experimental setup, and maybe to investigate the double scale porosity for the material with the FDM printing. Thank you.
Thank you, Alexis. Thank you for your presentation. Okay, Simon, can you? Yeah. Is there a question for Alexis before? Yeah.
Thanks for your presentation. I wondered how you choose the size for the cavities and the link.
Okay. This is mainly posed by the 3D printed techniques. We can go lower than for the small pores. We can't go lower than a certain dimension, and then we are targeting aeroacoustic application. So for airplanes, there are sample dimension that interested. It's 40 millimeters thickness layers. So this is a constraint for the definition of the geometry.
Okay, so there's not like a tuning like for Helmholtz resonators.
We studied the tuning. It appears, but because of the combination of the different structure, one behind the other, there is a coupled mechanism, and with more than 2 or 3 resonators, it is more complicated to calculate the resonance and to tune the